Welcome to the 25th lecture for the NPTEL course on computer system optimization for machine learning. As usual, today we will go over the recap, whatever we discussed in the last lecture, and then we will continue on basics of LLM. In the last lecture, we didn't finish the basics of LLMs. After that, we will discuss acceleration of LLMs. I think we will not finish the acceleration of LLMs in this lecture. We will continue in the next lecture. In the last lecture, we discussed about multi-headed attention. If you remember, again, we discussed the basic operations. So we first discussed about input embedding, then positional encoding, and then we discussed that attention is nothing but a function where it takes 3 input q, k, v, and then the attention function is just softmax of q, k transpose over square root of d, k multiplied by v, right. And then when we have multi-headed attention, then we first multiply this q, k, v with respect to, with corresponding weights. That means we multiply q with wq, k with wk, and v with wv, so that we can get this q prime, k prime, v prime. And then since it is multi-headed attention, we have to divide into multiple heads. So in this particular example, we have 4 heads. So we have divided q prime, k prime, v prime into 4 heads. So it is q1, q2, q3, q4, etc. right? And then we apply the attention function or attention formula on q1, k1, v1, q2, k2, v2, etc. so that we get the attention output for each of the head. Once we get the attention output for each of the head, then we concatenate to get the whole output. After that, we multiply with another set of weight, which is w0, and that's the final output of multi-headed attention. That's what we discussed yesterday, in the last lecture. Now, like why we actually needed this multiple head. So remember, whenever as a human being we analyze some sentence, we actually try to analyze different emotion of a sentence, right? Let's say you read a sentence in a newspaper, or nobody reads a newspaper nowadays. Let's say you read a sentence in some news in some app, and whenever you read that sentence, you try to analyze that sentence, like is it positive news, is it a negative news, is this news about politics, is this news about sports, etc., etc., right? Now similarly, this multi-headed attention actually tries to capture different context of the sentence, and different context means different head, or different head signifies different context. Okay. Now let's take one example. It's in the spirit that a majority of American governments have passed new laws since 2009, making the registration of voting process more difficult. And then there's a period, and then there is EOS, and then padding. EOS is nothing but end of sentence. Okay. Now if we do or if we perform multi-headed attention, multi-headed self-attention on that function, we will get some numbers. Okay. So let's say the number of head in this case is equals to 8. Okay. Now if that is the case, then that means we will get like before concatenation, let's say we will get like for each of the word we will get some output, right? So remember, before concatenation, let me go back, we have this 4 head where each of the size of each of the head is sequenced by this dv or dk, right? Dk is nothing but d model by the number of head, right? D model by number of heads. That's the size of dk, correct? Now let's see how to visualize this attention after we apply this multi-headed attention before concatenation. If we see the visualization, then it will look something like that. Now let's just focus on the multi-headed attention output of this word making. Now in this particular case, we will see the correlation of the word making with respect to all the other word in the sentence in different context. When we say in different context, that means we will see the value for different heads. Okay. Now in this particular case, you see that there are many colors, and some colors are bright, some colors are not so bright, some colors are not at all visible, right? So if you see, making this difficult has many colors which are visible, right? Now these colors are nothing but the output of different heads. Okay. Now if the colors are bright, if the colors are visible, that means making has a strong relation with respect to this particular word which is difficult in this case in that particular context. So, making has very strong relation with respect to difficult in many contexts, right. Similarly, making has a strong relation with this word more with in many such contexts. Now, you see that some colors are not even visible or not even there. If some colors are not visible, that means that making has no relation with more with respect to this particular context, right. Now, if you see making versus law, only this color is little bit visible, right, there is some color here, correct, but there is no color in this case. That means it has very weak relation in with respect to making has very weak relation with laws, and that weak relation is also with respect to one particular context. So, in this particular case we had 8 heads, that means we are trying to analyze the sentence, the input in with respect to 8 different contexts, and then some contexts are very much proper with respect to some between two words, and some contexts are not so visible or some not so prominent with respect to two words. So, that is how this attention works, or that is how this multi-headed attention works. Okay. I hope it was understandable. Then after multi-headed attention, there are other functions. I mean those other functions are already covered when we talked about DNN. We have batch normalization, that is similar to DNN again. I mean in batch normalization we just normalize each rows of the matrices, and then finally we have the decoder. Okay. Now, in decoder also you will see that we have similar types of functions or similar type of functionality like encoder. We have embedding. So, output embedding is similar to the input embedding. I mean again we have that embedding, I mean this embedding generates the embedding vector for each of the token. Then we have positional encoding. The same for positional encoding, we will apply the same function, and then there is something called masked multi-headed attention, which is same as self attention, but we will see there is some difference. Okay. And then again we have multi-headed attention. Now, here, so remember these are encoder decoder model, but most of them newer LLMs are decoder only model. Now, in encoder decoder model, if we have or once we have multi-headed attention in the decoder, then the keys and values k and v are come from encoder. Okay, these are k and v which are coming from encoder, but the queries are coming from itself, from the decoder itself. Okay. So, it means it is no longer self attention, but there is this is like cross attention. Okay. And then feed forward is a fully connected layer. So, we have this feed forward which is nothing but the fully connected layer, which is again we already saw in DNN, in the context of DNN. Now, as I told in the last slide, that decoder has something called masked multi-headed attention, right. Now, remember whenever we are trying to analyze a word, or whenever we are trying to not analyze a word, I mean whenever we are trying to generate a sentence. Let us say today, let us say we have a sentence, today is Wednesday, although today is not Wednesday. So, this sentence let us say needs to be generated. Let us say this sentence is the output of the prompt, right. Remember decoder gives the decoder provides the output, correct. Now, whenever we are performing the attention, or let us say the self attention, then whenever this word today is getting generated, it has no visibility on is and Wednesday, correct. So, it should not see the words which are coming next, right. So, that is why the goal is to make the model causal. I mean when we say model causal, that means it should not have any visibility on the future words, right. It makes sense. That means output at certain position can only depend on the words on the previous position. So, whenever this word Wednesday is getting generated, it should have visibility of is and it should have visibility of today. So, it should depend on the output which was generated in the previous position, right. So, the model must not see the future words, and if that is the case, then whenever we have the attention, then we should, or whenever we are computing the softmax. So, remember the attention function was softmax of q k transpose then square root of d k multiplied by v, right. Now, whenever we did this q k transpose, before applying the softmax, we should put the value of negative infinity for the future word with respect to a current word. So, let us say the word which has to be generated, or the sentence which has to be generated is your cat is a lovely cat. This word your, or this token your, should not have visibility on any of the next tokens, right. It should not see cat is a lovely cat. That similarly, the second cat should not see is a lovely cat, correct. So, that is why in those positions we put negative of infinity, so that once softmax is applied, the resultant output will be 0, right. So, that means we do not want to have any correlation with the future words, correct. Now, let us see how this inference happens with this transformer based model, right. So, let us say we have a translation task, where the task is to translate a English sentence to Italian sentence. Let us say the English sentence is I love you very much, and the Italian translation of I love you very much is ti amo molto, okay. Now, so again, if that is a translation task, then let us say, I mean, again, whenever we say inference, that means all the weights are trained and everything is proper, right. So, remember, initially we have to give SOS, start of a sentence, so that we can say the computer, or we can say the compute engine that now the sentence is started, and then at the end we have to give this token. These are specialized tokens. Start of a sentence and end of a sentence are the specialized token. End of a sentence is used at the end of a sentence, I mean, as the name suggests. Now, that particular sentence is provided as the input to this transformer, right. Now, to the decoder, again the first output has to be SOS, start of a sentence, right. Now, with this whole sentence, it will compute the self attention and everything, and then there will be cross attention, and then finally it will generate the word T, or it will generate the first token T, okay. Now, in the next step, this T will be appended with the input in the decoder. Now, another interesting thing is, we already generated all the encoder values for the input I love you very much, SOS I love you very much, EOS, right. That means we do not need to generate, or we do not need to compute them again, correct. So, we can cache it, I mean, we can store it somewhere in the in the memory, right. We will see more on this, but that is one compute optimization, that we are optimizing the computation, we are reducing the number of computation, right. Now, with that, and then when we have this SOS and T as the input to the decoder, with all this calculation, it will generate the next token, which is amo, and this process will go on. In the next step, this amo will be appended to the decoder input, and then it will generate molto, and then finally it will generate the end of a sentence. Whenever end of a sentence is generated in the inference, that means the decoding is done, right. So, that is how inference happens with the transformer based LLMs. Again, I mean, you can think that whenever you are putting some prompt or in the ChatGPT, then ChatGPT provides you the output one by one, right. I mean, it does not provide you the whole output at a time, right. So, this is the reason that ChatGPT or any other similar tool provides you the output one by one, like one output at a time, correct, because it is generating one token at a time, correct. Now, another important thing to note is, whenever the sequence length, the output sequence length is increasing, then all the matrix dimension, everything is also increasing, right. That means the computation is higher. That means whenever your output sequence length is more, the computation is more, and if the computation is more, if the number of computation is more, the time taken to compute all those things, or all those multiplication, addition, whatever, will also be higher, right. That is the reason, if you see, let us say if you have provided any of these agentic AI tool, let us say Claude, ChatGPT or anything, some input which has, let's say, long output. Let's say it's a description, or you just ask that write an essay on IASC, right? It is a long, it will have a long output, right? So as the time goes, you will see that the token generation speed gets lower and lower. The token generation speed gets lower and lower because it has more computation. I mean, of course, it's not exactly like that. I mean, we will see more nuances of increasing output sequence length, but for now you can think that with increasing output sequence length, the computation is more, and that's why your computation or the generation speed will be slowed down, right? Again, that's how inference of this transformer happens. Now let's see how the training happens. Okay, so far in the inference we assume that all the weights are trained, everything is proper, right? Now for training, remember we will have the input sentence, right? And then remember all the weights are initialized with like random number, all the weights are randomly initialized. Now the output to the decoder is shifted right. Okay, so the golden output is TMO mol to EOS, but the output to the decoder is SOS TMO mol to. What we are trying to say here is, whenever this English sentence is there, and then if the input to the decoder is SOS, then the output of the decoder will be T. If the input of the decoder is SOS and T, the output of the decoder will be AMO. So that's why the input to the decoder is actually shifted left, not right. I told it wrong. I hope you understood this. So again, I will explain it again. Input to the encoder is fixed. That's the English sentence. Now output of the decoder is TMO mol to EOS. Now we have to see the corresponding input to the decoder. Now this T will get generated when the input to the decoder is SOS, start of a sentence, right? This AMO will get generated when our input to the decoder is SOS and T, right? So now during training, or during the training process, what will happen? All the weights are initialized randomly, so it will calculate something, and remember that masked multi-headed attention is required here. So although we have provided the whole input to the decoder, but we will compute this masked multi-headed attention so that this SOS will not interact with TMO mol to, T will not interact with AMO mol to, and so on and so forth, right? The current tokens should not be interacting with the future tokens, right? Now again, going back to the inference, during forward pass, the encoder will compute something, the decoder will compute something, it will generate one error, and then it will perform this cross entropy loss with respect to this golden output, right? Now whenever we perform the cross entropy loss, we will get the error, and then we can do the back propagation to update the weights, right? So that's how this training happened. Now, like, the beauty of this is, so remember we had this SOS TMO mol to, and the output corresponding to SOS is T, output corresponding to SOS T is AMO, output corresponding to SOS T AMO is mol to, and so on and so forth, right? Now the beauty is, here during the training we are providing the entire input as well as the entire output at once, and the training process is happening, all the weights are updated, right? It all happens in one time step, unlike RNNs. So if you remember, in RNNs we have multiple of those blocks, and then we have input and output. So if you remember, the backpropagation used to happen in RNN at one block at a time, right? Sorry, one of these RNN algorithm at a time. So if we have a sequence length of n, that means we have n of these RNN blocks, and then we have to backpropagate one step at a time, and that's a time taking process, right? So that's why the training of a transformer model happens at one time step, and that's a huge benefit with respect to RNN, because if we can perform the training at one time step, if we can perform all the computation in one time step, we can leverage parallelism of GPUs and all those things to accelerate the computation, but given that we have GPUs, we can perform this in one time step, unlike in RNN. Like in RNN, although we have GPUs and all those things, there is no way we can actually do some parallel training, or not. I mean, when I say parallel training, I mean even if we have parallel computation, that will not help much for RNN training. Okay. So that's the biggest benefit of these LLMs. I mean, then what happened now? That means now we are able to train like trillion parameter model in almost the same time, and that takes probably almost the same time as a million parameter model of RNN, right? So that means now we are capable of like training a large or very large model. Again, very large model means that will perform many tasks very accurately, correct? So that's why this attention based transformer model became very popular, and all the companies actually adopted these transformer models for to making these all these agentic AI tools, right? So yes, I mean I am sure that you all use all these agentic AI tools like Cloud A, ChatGPT, Gemini, Copilot, etc. But you should know like why suddenly, what's the magic? Suddenly they are being very popular, right? Now with that, let's see some acceleration technique of LLMs. So you might already figured out that, I mean, there are too many multiplications, additions, etc. is happening in the inference of LLMs, right? Of course, in training in LLM also it happens, but inference is a thing which is done like again and again, correct? Now, I mean, remember, I mean, all the attention computation has nothing but matrix multiplication, and then if we have this encoder decoder based model, we don't have single encoder or single decoder, we have multiple of them, right? So just to give you a context, let's say, I mean, Quen I think has 24, I mean, okay, it's a decoder only model, but I think the larger version of Quen has 24 decoders. Then the embedding size is maybe in terms of 8K, the maximum sequence length is also in terms of like 16K. So all the matrix dimensions are very high, right? So there are too many matrix multiplication, too many multiplications in general. So Linformer is one of the technique which reduces the complexity of attention to order of n. So if you remember, when we are computing the head, one attention head, that is nothing but attention of QWK, QWIK, KWIK, VWIV, right? And which is nothing but softmax of QWK, KWK transpose over square root of DK multiplied by VWV, right? Now computing this inner matrix P is expensive, and if you look closely, it will be capital of N. If you look closely, it is of complexity of order of n square, where n is the embedding size. Okay. Now in this particular paper, so by the way, Linformer is a paper, you should go and check the paper. In this paper, the authors made one crucial observation, that they made this observation that self attention is low rank. So whenever they say low rank, that means many rows of this P, this inner matrix, is almost dependent to each other. If that is the case, then we can perform singular value decomposition so that we can bring down the matrix multiplication order. So what they mean is, we can, instead of performing the exact attention, we can introduce this E and F projection matrices of size n by k, where k is very less than n. Okay. And then our attention computation will look like QWK multiplied by E KWK over square root of DK, softmax of that multiplied by Fi VWIV, and then the dimension of the inner matrix becomes n by k. Okay. So by mistake I wrote all the n in small, in lowercase, it should be uppercase n. Now the computational complexity now reduces from order of n squared to order of nk. So in that paper you can see there are theoretical derivations. They argue that k is in the order of d over epsilon square, where d is the embedding size and which is independent of n, right? The sequence length is independent of n, correct? So, now if that is the case, that means we can say that this order of nk is almost similar to order of n, right. Now, again, I mean, if we can say that, that means we are reducing the complexity of this matrix multiplication from order of n square to order of n. Again, there are like theoretical derivation, please go over the paper and you will see the theoretical derivation yourself, but the main crunch of the work is they are reducing this complexity of this inner matrix from order of n square to order of n. Now, let us see some results. So, whenever we did some optimization on these computation, we have to first show that the accuracy does not change, and then we have to show what is the benefit in computation. Okay. So, first let us see the accuracy. So, they say they show the accuracy with respect to the vanilla model. So, they show in 3 cases where n is 512, 2 cases, n is 512 and 1024. You can see, I mean, I will not go into the detail of this table, they are showing the accuracy for different data set. You can see that even if they apply this Linformer, for Linformer also they have different version, the accuracy is almost the same as the vanilla accuracy. So, the first row is the accuracy with the original model and the other rows are the accuracy with Linformer, various version of Linformer. You will see that the accuracy is almost same as the original model's accuracy. That means it does not affect the accuracy much. Now, let us see what is the improvement in efficiency. So, whenever we talk about efficiency, we need to say what is the amount of time saved, which is nothing but the reduction in latency, and what is the savings in memory. So, remember all this, I mean, we will anyway do some memory calculation, but remember one thing, that whenever we have this attention based computation, it takes huge amount of memory, right, because all those activations, weights has to be stored somewhere, right. Now, first they are showing the amount of the reduction in latency. So, this particular axis, this particular column is showing the length, sequence length, which is varying from 512 to 65536, and then all the numbers are shown what is the time saved for the different projected dimension. Now, of course, if we project in a lower dimension, the time saving will be higher. So, for an example, if our original sequence length is 16384, then you can see if we do a projection dimension as 256, then the time saved, the reduction in latency is 7.8. Now, if our projection dimension is lower, let us say it is 2048, then the time saved is even lower, right, because of course, we are doing even less number of computation, right. So, the k is becoming lower, right. Sorry, I just mixed up. So, I mean 2048 is the higher, but I mean overall what I wanted to say is there. So, if we project onto 2048 dimension, the time saved is 3.3, but if we project into lower dimension, then our time saving is higher, 7.8, right. The similar story is there in the memory saving also. If we take 16384 is the original sequence length, and then if we project onto the higher dimension, we have 8 times, if we are saving the memory 8 times, we are having 8 times memory saving. If we further project into lower dimension, then we have 48 times saving in memory, right. So, overall you can see these numbers are very promising, right. 8 times saving in memory, 3.3 times saving in latency is like very good, and you can think that something which was taking 1 hour, now it will take like 15 minutes, correct. So, as you can see that with this Linformer, there is not much change in accuracy, but then there is huge savings in time as well as memory, right. So, with that, let us conclude this lecture. Thank you very much for your attention, and in the next lecture we will continue with some more accelerator and some more computation technique for LLMs. Thank you.